Hello class, this is Mrs. Ayodeji with today's video on 11.2 slope fields. As you're watching the video, please write down important vocabulary, formulas, equations, and feel free to pause, rewind, and replay the video as often as you need so you can get a clear understanding of what is occurring in the video. At the conclusion of watching the video, write down a brief summary of what occurred in the video and submit that summary via the online WISC form as well as a top question. All right, let's begin. Today we're going to talk about slope fields, and interestingly enough, slope fields was not part of my calculus curriculum when I was in school. So I very recently learned about slope fields, and it is a way to which you can solve differential equations, another format of solving differential equations. So let's begin. So let's start with an example of a simple first order differential equation. dy dx is equal to y. And as you can see, it is a differential equation because it involves a derivative of a function as well as a function, and we're going to call the function y. But what does this actually mean in this particular situation? It means that, let's say y is equal to f of x. It means that given any xy point that's on the function on the function f, the slope of the tangent line at that point is going to be equal to the same value as y is. So at each point xy on the function, f of x equals y, the slope of the tangent line to the function of f at x is the value y. Well, what is that going to look like? How are we going to be able to represent that? So let's just pick a general point, xy point, and then draw a line segment to indicate the slope of the tangent line at that point. So I'm going to use the point -1, 3. So -1, 3, -1, 1, 2, 3. So here's the point -1, 3, and the y value is 3, which means the slope of this tangent line of the function at that point is 3 as well. Okay. If you notice, though, we will have the same looking slope of the tangent line at any point on the y equals 3 line. So let's represent that. Hold on a second. So I just make a whole bunch of copies. And I'm not going to do this because it will take up time. So let me just pause the video while I include those. And it goes on forever and ever. On the line y equals 3. So it doesn't matter what the x value is, the slope of the tangent line is always going to be 3 because the point is on the line y equals 3. Let's use another example. Let's consider the point 2, 0.5. So that means the slope of the tangent line is 0.5. So we go to 0 to 0.5 and look something like this. But not only is it that the slope of the tangent line at that point is the slope for any point on the line y equals 0.5. Okay, and it looks something like that. And then let's take a look at another example. Let's look at the point 6, -1, which means for the point located at 6, -1, 2, 3, 4, 5, 6, 1. The slope, is -1. But it's not only just the slope of the tangent line is -1 for this point, it's at the point for any point on the line y equals -1. Sorry, I was in the wrong position. I moved it over. So this is the case for any point on the which has a y coordinate on -1. We can sit up here and do this forever and ever and ever for any point on this line. So if we were to do this for every single point on this grid, we would have a bunch of little line segments that represent the tangent lines at that particular point. Well, what would that look like if we took away all of the green points and just left the tangent lines? Well, it would look something like this. And this is the slope field for the first order differential equation dy dx. And as you can see, it looks very similar to something I had over there. Now, why are slope fields useful? Well, if I have a slope field for the differential equation, I can get an idea what the graph of the general solution will look like based off this slope field, because I can just start at a point and then just continue on. As you can see, you can even see the shapes that it looks like. If I just continue on, I cannot draw, but it looks something like this. Or it can look, if I start down here, it can look something like this. A bunch of different solutions because I obviously cannot draw. But that looks very familiar. That looks like an exponential graph, which it is, which makes sense because the general solution for this differential equation is an exponential function, because just think of it. What function has its derivative to be the same as the exact function? And that, of course, is the exponential function. So if you have the slope field for a differential equation, you can get an idea of what the graph looks like and therefore get an idea about the general solution of the graph based off of the differential equation. So let's look at some other examples of slope fields that are given in your book and see if you can get an idea about what the general solution will look like. So in this case, we have a slope field for the differential equation. Again, first order, dy is equal to 2x, dy dx is equal to 2x. And as you can see here, based off how this slope curve looks, if I was just to pick a point and continue around in the direction of the tangent line, I would get what looks like, gosh, I cannot. Looks like a parabola, which we know a quadratic equation produces the graph of a parabola, which means that if we were to take the derivative of a quadratic equation, it would be a function of x. I'm sorry, it would be a linear function, which makes sense here. And actually here they have a better drawing, so you can see the better drawings from that. Okay. All right, so let's take a look at another example. This is example 2, using the slope field, guess the form of the solution curves of the differential equation. Okay, so here we have differential equation, negative x divided by y. Well, what does that mean? Well, let's consider the point 0, 0. What would be the slope of the tangent line at that point? Well, we use the differential equation, so it would be negative 0 over 0. Well, that is undefined, so we can't use that. So let's try another point on the x-axis. Let's try 4, 0. And so what would be the slope of the tangent line at that point? Well, it would be negative 4 over 0, which means it's undefined. The slope is undefined, which means that we have here a lovely vertical line, okay, which is not that interesting enough. But so let's try a point on in two slope field formation, any point on the x-axis, because the y value is 0, is going to have an undefined slope of the tangent line, which means you're going to have a whole bunch of vertical lines at these points. So let's try a point that's actually on the y-axis. So another point besides origin. Oh, did I put that there? I didn't even put that there because this should not be there. That's undefined. Sorry, put that over there. All right, over here we have 0, 4. So when we put this into our slope formula, differential equation, we have negative 0 divided by 4, which means the slope of the tangent line is 0. So it's a horizontal line. So we're going to move that right over here, and it would look like this. And in fact, every point on this y-axis, when no matter what its x-coordinate is y-coordinate will always, no matter what its y-coordinate is, its x-coordinate will always be 0. So we're always going to have a 0 slope of the tangent line for any point on this y-axis. So the slope field for these points will look something like this. So now we would be here all day trying to figure out what the slope field is going to look like, but we're trying to be strategic and not spend a lot of time. So let's think about what's going on. We're having undefined slope all the way to 0 slope. So what's going on? It seems like the slope, of course, would be decreasing here. For any point over here, the slope would be decreasing, so it would be less steep. And then we're going from a slope of 0 to a slope of undefined over here in this quadrant, which means the slope would be increasing. But it's not going to be increasing in the way you think, because remember it's negative, so we change the sign. And so what will this look like in the end? It looks something like this. And some of you may recognize automatically what the general solution of this slope field would be. It will be, of course, a circle. Okay, x squared plus y squared is equal to 1. And you could differentiate that implicit equation to end up with a first order differential equation of negative x over y. Okay, and very quickly, if I want to be able to use a slope field to find not just a general solution, but a particular solution, then I need extra information besides just the differential equation. I need a point that is either on the function or a point that satisfies the differential equation. And if I do, then I'll be able to figure out what the particular solution is of this case. So example, I can't remember 3 or 4, example 3 says, let's use different conditions. Okay, so the first condition, we're not going to have time to do them all, but what if y is equal to 0 when t is equal to 0? So in other words, we have the point 0, 1. Okay, and this is right here on this one. It's about here on this one. Okay, it's about one way. So that lets us know that we can draw a curve based off of the way the slope field is going, where it goes through this. And this, based on the slope field, is going something like this. Gosh, I cannot draw. And then for this one, it looks like it would be going like this. So this would be the particular solution because it satisfies the differential equation by being on the slope field, but then it goes through this particular coordinate point 0, 1. And if we want to do it for other conditions, when y equals 0 and t equals 1, or when y equals 3 and t equals 0, we'll have our solutions looking in the format like this in this case. Okay? And so that's how we would use this. Now, will we always be guaranteed to have a solution, a particular solution for every slope field? Yes and no. It depends on the slope field. If the slope field is continuous, then that means you're always going to be able to pick a point and then draw a particular solution through that point based off the slope field. But if the slope field is not continuous, you may pick a point that's in the part of the slope field that's not continuous, and then therefore there will be no solution. And we'll look at examples of that in the future. Okay, that's it. I hope you enjoyed it. I enjoyed teaching it or making the video on it. See you in class.